Thank you. So I'm Yokoi, and this is joint work with Yasushi, Kawase, and Yutaro Yamaguchi. And in this work, we propose a new game, which we call sequential matching game. So this models a decentralized market in which firms sequentially make offers to potential workers. So an instance of this game consists of I and sigma, where I is an instance of one-to-one stable matching. So I consists of the sets of firms and workers and possible offers, and each firm and worker has a preference over possible partners. And we also have sigma. So this is an offering order representing a schedule of offering. And this is consistent to firms' preferences. So this means each firm makes offers from the top to the bottom of preference list. And these are market rules. So in our model, firms are not strategic. They just follow a prescribed offering schedule. And workers can be strategic. So once a worker receives an offer, she should decide whether to accept or not immediately. And the decision is irrevocable. And if an offer is accepted, then that firm and worker are matched and they leave the market. So for example, in this case, first firm P1 makes an offer to worker Q1. And here Q1 has two options, accept or reject. And if they accept, then her job at this firm P1 is guaranteed, but at the same time, she loses the chance of getting offer from her favorite firm P2. But whether she will get an offer from P2 depends on the actions of other workers. So to decide best action, each worker has to predict the behaviors of other workers.
What do each worker know about other workers?
So each worker knows all information.
All the information.
Yes. So this situation can be formulated as an extensive game. So each round of the game corresponds to each offer. And the player who takes an action is the worker who gets an offer. And here, as I said, so here we assume that workers know the offering order and preferences of others. So this is an extensive game with perfect information. And if the first offer is accepted, then the pair P1, Q1 are matched and they leave the market, and the game continues with remaining 4 agents. And if the first offer is rejected, then just an H P1, Q1 is eliminated, and both P1, Q1 stays in the market, and the game continues with these 6 agents. And considering all possible scenarios, we can draw this game tree. And each leaf of this tree corresponds to some matching. So for example, this leaf represents a matching obtained when the game proceeds along this green path. So first, the offer P1, Q1 is accepted, and the next offer is rejected, and the offers P2, Q3, and P3, Q2 are accepted. So we obtain this matching in the outcome. And each worker's preference over outcomes depends only on her partners in the outcome matchings. So for example, here, now Q2 gets an offer from P2, from P3, and if Q2 chooses accept, then her partner in the outcome is P3. And if she rejects, then she will be unmatched in the outcome. So here, accept is her best action. And in this way, we can define the best action for each round. So suppose we can define by backward induction. So suppose we have already checked the best actions for this red node, and let's next consider this point, then here Q2 gets alpha from P2, and if C accepts, then her partner in the outcome is P2, and if C rejects, then her partner is P3. So it is better than P2. So here, reject is her best action. And finally, we obtain the set of best strategies. And note that at each round, the best action is defined uniquely, because once a worker rejects some offer, so C will never get the same offer again. So different actions result in different partners in the outcome. So best strategies are defined uniquely.
Firms do offers in sequential order of their order?
Sorry?
The firms offer in a
Yes, yes,
order of
yes. Prescribed. They just follow prescribed schedule. And when all workers follow their best strategies, then we obtain this matching. So this is a reef obtained when the game proceeds along this red path. So we call this resulting matching as SPE of I sigma, or the SPE matching. And we are interested in this matching. So first, we expected that this matching can be explained by some familiar notions in stable matching theory, because this is a game played on stable matching instance. But unfortunately, it is impossible. So it turns out that the SPE matching can be unstable. So this is a previous example. And here, green edges form the SPE matching. And we can find blocking pair here. And this fact gives a sharp contrast to previous works. So there have been proposed several settings of sequential matching, but in those works, an equilibrium is unstable matching. So the situation is very different from the previous works. And also, we can observe that even weaker stability fails in the SPE matching, and also SPE matching changes depending on the offering order sigma. So this fact implies the difficulty of capturing SPE matchings in our model. So we are now interested in whether we can compute the SPE matching efficiently or not. So as we saw, the SPE matching is well defined by backward induction. Sorry, please.
So does it always exist in ordering such that you get a stable match?
That is a good question. That is our future work, and I will mention that problem later. So yes, so now we are provided some fixed order, and we want to find SPE for given I and sigma. And yes, so that SPE is defined by backward induction, but it requires exponential time. So we want to compute it in polynomial time. And if it is possible, then each worker can choose the best strategy, and so we can predict the outcome of the market. And for this question, we provided a dichotomy theorem. So this characterizes the complexity of computing the SPE matching by the maximum length of preference list. So as a positive side, we show that the SPE matching can be computed in polynomial time if the preference list of firms are of length at most 2, or those of workers are of length at most 2. So this says the problem is tractable if the list length is bounded by 2 in one side and unbounded in the other side. And as a negative side, we show that all other cases are p-space hard. So that is, the problem is p-space hard even if the preference list of all firms and workers are of ranks at most 3. So we call these cases 2 infinity type or infinity 2 type or 3-3 type to distinguish them. And I first explain the p-space hardness of 3-3 type. So this is shown by reduction from quantifier 3-sat. So this is a standard technique to show the p-space hardness. And as we saw, so the SP matchings have irregular structure. So because of that, we can construct various gadgets, like OR gate and not gate. So combining these gadgets, we can achieve the reduction. And I next explain the tractability of these 2 types. So we show it by providing algorithm to compute SP matching. So here we introduce some notations. So first, by QOPT we denote the Q-optimal stable matching of the matching instance I. And also for a pair E consisting of P and Q, we write I sigma slash E to mean an instance obtained from I sigma, deleting P and Q and all related offers. We call this operation the contraction of I sigma by a pair E. And now algorithm is described like this. So we call it a Q-oriented SFDA. So here SFDA means sequentially fixing deferred acceptance. So this algorithm first initializes the temporary instance by provided instance and set the temporary solution to be empty set. And repeats the following procedure. First, compute the Q-optimal stable matching. And among all the matched pairs, take the one that is scheduled to be offered earliest by sigma, and call it E star, and add it to the current solution M, and update instance by contracting that pair E star. So this algorithm repeats finding the Q-optimal stable matching and fixing an edge that is smallest in the offering order. And we can observe this algorithm runs in polynomial time. And this is the proof sketch for the correctness. So we show that the output of SFDA algorithm coincides with the SP matching for any instance of these 2 cases. And this is shown by induction on subgames. So recall the structure of this game. So when the first offer E is accepted, then the pair PQ removes the market and we obtain smaller instance. This is again an instance of sequential matching game. And also when the first offer is rejected, then again we have another instance of sequential stable matching. And assuming this equality for these 2 subgames, we show this equality for the original instance. And now I conclude my talk reviewing our result. So we show that the SP matching can be computed by the algorithm sequentially fixed deferred acceptance if the preference list of firms or workers are of length at most 2. And here we remark that this result holds for a general offering order. So in this talk, I use example in which each firm makes all offers successively. But our model allows any offering order that is consistent to firm's preferences. And our tractability results holds for general offering order. And we also show that the problem is p-space hard for all other cases. And this hardness results holds even if the order is restricted to be position ordered. And as one of possible future directions, we are now interested in designing offering orders so that the outcome becomes stable. So as we observed, the SP matching changes depending on the offering order. So we expect that we can reach the outcome into stability by designing the offering order well. And now we conjecture that for any matching instance I, there exists a position ordered offering order sigma, such that the SP matching is a stable matching of matching instance I. And actually, we already confirmed that this conjecture is true if we have no restriction for position ordered. So if we can use general offering orders, the stability can be achieved. And it is open that whether we can achieve the stability with the restriction when sigma is restricted to be position ordered. So we haven't found a counterexample, and we now believe this statement is true. And this is the end of talk. Thank you.
I was wondering, your algorithm, you said it would work if we have two preferences on either side?
Yes, yes, yes.
If we have, suppose, two preferences on one side, but like, so let's say constantly many are not two, they are more than two. Like few of them are more than two. Would it, do you think it would extend based on how many are not more than two? Like, I was trying to understand where exactly you use the fact that it's two, and maybe, I mean, I need to know probably more details about the analysis to understand that, but I just wanted to know if you have thought about it.
It is not so simple to extend our algorithm to for that case,
Okay.
but yes, but we haven't considered so much. So yes, thank you.
Okay, that's fine.
Thank you.